So this is the main goal, is to look at angular and tangential variables. And when I talk about angular variables, I'm talking about these rotational variables. Tangential variables looking at a distance along the surface of your circle. So we had displacement, velocity, and acceleration both in angular and tangential. And we have units that look similar: radians, radians per second squared, meters, meters per second squared. So this might be an indication that there might be some relationship between these two variables that is not readily apparent at this point. They're clearly consistent in terms of how they're defined within each side, that velocity is the change in displacement, acceleration is a change in velocity, angular velocity, change in angular displacement, angular acceleration, change in angular velocity. We also ended up with two sets of toolbox equations which look relatively similar to one another. In fact, they look exactly the same, except for the fact that you have angular variables versus tangential variables. So let's look at, is there a connection between angular and tangential? Is there a connection between angular velocity and tangential velocity, or angular displacement and tangential displacement, or angular acceleration and tangential acceleration? And the way to start to think about this is to think about, what is a radian? What does this measure actually mean when we talk about it to measure an angle? Now, most of the time in physics when we've dealt with angles, we've dealt with them in degrees. This is one of the few instances where we deal with angles in radians. And there's a very specific reason why we would deal with an angle in radians in this case, and that comes back to, what is a radian? What a radian is if we've rotated from this line to this line such that the distance along this arc is the same as the radius of your circle, then that is 1 radian of angle. It's worth pointing out that in one circle you have 2 pi radians. So what this gives us is that there's a connection between x, this tangential displacement, radius, and that angular displacement. And it looks like this: x is equal to radius times this angle in radians. So if this was 1 radian, x and r would be the same. If I went one time around the circle, well, I know that the distance around a circle is 2 pi r. Well, it must be 2 pi radians. Now, it's worth pointing out that if we do this and actually carry this through my toolbox equations, we get a relationship for angular velocity and tangential velocity that looks like this. Tangential velocity is equal to radius times angular velocity, and the same relationship between tangential acceleration and angular acceleration. Tangential acceleration is equal to radius times angular acceleration. Now, I'm not going to spend time in this lesson video deriving those equations. You can certainly do them on your own. They're not that hard to do. Easiest way to do it is to just say, well, v is equal to change in x over t. What does that actually mean? And work it out. But we can actually use the consequence of these ideas to actually figure out what's happening in a situation. So you have a spinning disk, and I'm going to say point B has a radius that's twice that of point A, and I want to know, what is the ratio of tangential velocity at point B to tangential velocity at point A. Now, it's worth pointing out, if both point A and point B are on a spinning disk that's spinning at an angular velocity of omega, they both have the same angular velocity. Their rate of rotation is the same. However, how fast that object is moving is going to be different. We can probably say, just by looking at this situation, if it's going to take, let's say, a second to rotate once around the circle, B has to travel a lot further than A. So let's actually work this out. We're looking for the ratio VB over VA, and I know V is equal to R times omega. Well, VB would be RB over omega B. VA would be RA over omega A. Well, remember I said omega B and omega A are the same. They're both on this spinning disk. We know that the radius of B is twice that of A, so if we substitute that in, what we'd find out is that B is moving twice as fast as A, that ratio is 2. Another example problem that's a fun example problem to do is what I call the gears problem. And you see gears like this in lots of different places. Probably the most common place you've dealt with this is on a bicycle. You know that there are different sizes of gears on both your pedals and on the back wheel. And by varying those different sizes, it becomes easier or harder to pedal at different types of speeds. So here we have two gears shown below. The one on the left has a radius of 30 centimeters. The one on the right has a radius of 10 centimeters. I'm going to say the angular velocity of the gear on the left is 3 radians per second. So this thing is rotating at 3 radians per second. So you can imagine me pedaling this gear. What I want to know is, what is the angular velocity of the gear on the right? So these are the known pieces of information that I know. Now the one thing I can say is the tangential velocity of the chain around this gear has to be the same as the tangential velocity of the chain around that gear. That's because in order for this chain to be a constant chain, it has to be moving at a constant speed. So the velocity of whatever the chain is going around here is the same as the velocity of the chain going around here. Tangential velocity for both gears is the same. Now this means that I can actually come up with a fairly quick ratio. That omega 2 is going to be equal to R1 omega 1 over R2. And so we get that omega 2 is 9 radians per second. The small gear is rotating 3 times as fast as the big gear. So this is sometimes called gear ratio, if you've ever heard of that term, that 3 to 1. That's basically going to tell you, if you have a chain between those two gears, how fast is the smaller one moving compared to the larger one. Now it's worth pointing out that if I knew something like how big the bike tire was, I could then figure out how fast your bike is actually moving from this piece of information. So it's kind of a quick overview of how tangential and angular velocity relate to one another, or tangential variables and angular variables, and how we can interchange between the two depending on the situation. And we want to